Right, so this will be chapter 5, and this chapter is called Chemical Accounting because if you've ever tried to balance out your expenses and what you're making every month, which hopefully you are, that's called accounting, right? And it's a very, very similar concept. And in fact, you'll almost feel deja vu whenever you do this for a chemical equation, okay? Because you have expenses coming out, which are things getting made into products, and you have things going in, which is what you start with, what you're given, what you're mixing together. All right, so the chemical equations are going to represent the sentences in the language of chemistry. They're communicating to you a chemical change using symbols and formulas to represent the elements and compounds involved in that chemical reaction. They're much like math and how it's representing the world through equations. It's just that we have more symbols rather than numbers. So reactants are going to be the species present before the reaction. Products are going to be the species present after the reaction. An easy way to remember this is you produce products, reactants are what you use. So reactants will produce, yield, products. This arrow right here, this represents a yield, or you can say this is reacts, to form, if you will, or to produce. Now, in chemical equations, we have some symbols and you need to understand what they mean. So these following are used to denote the state of a species, meaning one of the reactants or products, in an equation. And so we have solid, which is parentheses S. Notice the small s. This is to help differentiate them from the identities of the chemicals, things like carbon, sulfur, etc., the elements that you'll see. We have L, so parentheses L, this is going to be a liquid. And we have parentheses G, gas. Now, those are the phases of matter you've talked about and seen before, solid, liquid, gas, of course. Finally, there's aqueous solution. Now, this is a special one because it's actually a solution. It's going to be anything dissolved in water, okay? So when we say an aqueous solution, that's what we mean. If we say O2, AQ, it would mean O2, the gas O2 that you breathe, is dissolved in water. And this is actually what fish breathe. It's aqueous O2, okay? All right, coefficients. These are going to be the number used to balance a chemical equation. You can never change your subscripts. Remember, the subscripts actually tell you the chemical identity. They tell you what compound you have. So for example, why did the chemist go to jail? Well, the chemist was talking to his friends and decided to go off to another room. He called back to his friends, "Hey guys, you want some H2O2? And his friends go, yeah, I'm thirsty. And so the chemist brought them H2O2 in glasses, and they went ahead and just drank it. And of course, the chemist panicked and, ended up having the police called in because all his friends died because they drank hydrogen peroxide. So that joke is moderately funny, hopefully. Hopefully you got a little bit of a chuckle out of you. But it does a great job of representing the importance of chemical compounds. His friends thought he said, "Do you want some H2O as well?" What the chemist said was, "Did you want some H2O2, which is hydrogen peroxide?" So H2O is water, H2O2 is hydrogen peroxide. So if you try to change the subscripts in a compound, it is a completely different compound. Much like CO2 is different than alcohol, which is CH4, CH3, CH2OH. And it is different than methanol, which is CH3OH. Notice that slight differences in those numbers, those subscripts, give you completely different compounds. It could give you something you need to survive. It could give you a poison. It could give you a gas instead of a liquid. It can be completely different in almost every property that you can imagine. So, the importance of these subscripts cannot be overstated. Also, keep in mind that chemical compounds, I'm going to repeat this from an earlier thing because it's so important for you to understand about chemistry. Chemical compounds are chemical compounds. Water is H2O. It doesn't matter where the hydrogens and oxygen come from. If they're bonded together as H2O, that is water. So water that comes from you, water that comes from your car, water that comes from a factory, water that comes from the rainforest, all of those are the same. There may be different things dissolved in that water, but the water molecules are the same no matter what. Okay? And that means that when you hear things like the CO2 that comes out of a car is more poisonous or dangerous to the environment than the CO2 that comes out of living organisms, it's total bullshit. It has no grounding in fact. It is just complete crap. Okay? If it's CO2, it is CO2, period. That is the same compound. On the other hand, if you write CO, that is carbon monoxide. That is actually poisonous. It's a poisonous gas, and how people, you've probably seen people like try to kill themselves with cars, or seen a scene on TV at least, where they run the car in a garage, which is not easy to do if you have a new car. But anyways, that's because of carbon monoxide. Okay, a new car has a catalytic converter in it, and catalytic converters typically will convert all the carbon monoxide into CO2. And so it's almost impossible to do with a new car. You have to have a kind of beater that is, failing its emissions tests to actually do that. But anyways, it's not easy to do. Okay, so this shows you a chemical equation that's not balanced yet. So if you were to balance this, what you do is you put numbers in front of these to represent the fact that I have, maybe two H2s. So two molecules that are hydrogen bonded to hydrogen. Okay? Much like the difference between having two Twix bars versus having one Snickers. Okay? You can't change the subscripts. It changes the type of candy, if you will. I guess Halloween's giving me candy for examples now. All right, so let's see some examples of somebody doing this incorrectly. Let's see an example of somebody doing it correctly to balance this out. Keep in mind, another way of thinking about these chemical equations is they can also be thought about as recipes. They're much like any other recipe you talk about. You put one hot dog with a hot dog bun, and you'll get a hot dog for somebody to eat. You put a hamburger with two buns, two sides of a bun, and you're going to get a hamburger for somebody to eat, right? That's a recipe. So if we do this, notice that we have too many oxygens on this side. We don't have enough over here. We would not have enough oxygens represented, and thus we have said that mass has been destroyed or created. That can't happen. So to do this correctly, you would put a 2 in front of here and a 2 in front of here. That would balance out the number of each element on both sides. So you have 4 hydrogens here, you have 4 hydrogens here. You have 2 oxygens here, you have 2 oxygens here. That is done correctly. That is correctly balanced. Let's look at something done incorrectly. So here we see an example of we went ahead and put a 2 here. Well, now that's actually hydrogen peroxide. That's not water. You've just killed the chemist's friends again, didn't you? Let's look over here. Well, here we went ahead and just added a single oxygen. But that wasn't a chemical species in the reaction. We've just added something that never existed. We can't do that. We need to balance the numbers of the compounds in this. It would be like saying that I put flour and sugar together so I get cookies and a possum. That doesn't make any sense, right? It's just silly. And when you do this on a chemical equation, you're doing the same thing. I'm putting hydrogen and oxygen together. I get water and some species that totally doesn't even exist. Okay? I get a magic unicorn, if you will. All right, so the law of combining volumes. When all measurements are made at the same temperature and pressure, the volumes of gaseous reactants and products are going to be in small whole number ratios. So for example, if you were to put together 4 volumes, we can call these liters if you would like, but again, it works for any volume measurement. So 4 volumes of hydrogen, or 3 volumes of hydrogen, and 1 volume of nitrogen, that would give you 4 volumes of gas. Now, these react together to give you only 2 volumes of the ammonia. And the reason for that is the chemical equation. You have 4 volumes of this gas here. You're only going to produce 2 ammonias for the 3 hydrogens and 1 nitrogen here. So Avogadro's hypothesis was when measured at the same temperature and pressure, volumes of all gases contain the same number of molecules. And so the reason that you only got 2 volumes out of this reaction was because these 4 molecules would have only given you 2 molecules of ammonia. It's kind of like when you tape stuff together, right? So when you combine, let's say we're playing with Legos here, okay? That's something we've all probably done before. And so we have 3 pieces of those square Legos, and we have 1 sheet. We combine them together, and we get 2 pieces here, okay? So we end up getting only 2 pieces of our Legos because they've been clipped together, haven't they? Now, that's because the individual parts could be combined in such a way. That's the molecules, Avogadro's hypothesis. Now, Avogadro's number is actually kind of a little trick that he played to make 2 things work together. And so first, Avogadro's number is defined as the number of atoms in a 12-gram sample of carbon-12. And this number is 6.02 times 10 to the 23rd. So if you have 12 grams of carbon-12, which is one of the isotopes of carbon, so 12 grams of carbon, if you will, then you're going to have 6.02 times 10 to the 23rd atoms of carbon in that sample. This was done so that that number on the periodic table can represent the number of grams in a mole of carbon, which I'll get to in just a bit, and it can also represent the individual masses of carbon atoms, because obviously they didn't know what masses of atoms would be when they made the idea of a gram. That wasn't something they would have been aware of. So what is a mole? I want you to think of moles as packages, okay? So you're probably all somewhat familiar with having a package of a dozen pieces of bread, or a dozen buns, or whatever. And so mole is like a package. But instead of saying a dozen, and dozen means 12, right? We say mole, and mole means 6.02 times 10 to the 23rd individual pieces. So let's try this with the dozen first, and then we're going to give the same example with moles. So let's say we have a dozen pennies. When I say a dozen pennies, your head goes 12 pennies, doesn't it? And you understand that intuitively because you've been trained, which is what I'm trying to do with a mole. And so if I say dozen pennies, 12 pennies. If I say dozen humans, 12 humans. If I say a dozen molecules, that would mean 12 molecules. So now we have a mole. A mole is going to be, if you have a mole of pennies, you would have 6.02 times 10 to the 23rd pennies. If you had a mole of humans, it would be 6.02 times 10 to the 23rd humans. You had a mole of molecules, it's going to be 6.02 times 10 to the 23rd molecules. See, it's just like a dozen. It's a package that represents a certain number of things in it. Okay? By the way, there's something called Mole Day, which is 10/23, October the 23rd. It's actually why, if you notice, there was like events on the campus that was being hosted by SMACS on October. And that's because Mole Day, 10/23, the sort of thing is you sort of celebrate a little bit of chemistry stuff, and typically you go ahead and figure out what a mole of different things would be. Okay, so for example, a mole of baseballs would be 6.02 times 10 to the 23rd baseballs. If you were to figure out the mass of that, you'd figure out that the mass of that mole of baseballs is actually about the mass of Earth. So if you had a mole of baseballs, it would be Earth sized planet of baseballs. If you had a mole of drops of water, it would be about the same mass of the oceans, all the oceans on Earth. And so that number is an extremely large number because individual molecules and atoms are so small. So if we want to work with something reasonable that we could actually manipulate easily, we have to typically work in things that are, about a mole of the molecules or atoms. So formula mass is going to be the average mass of a formula unit relative to that of carbon-12 atom. So it's simply the sum of the atomic masses or all atoms in a formula. So literally you just take all the atoms that show up in a formula, you look on the periodic table, you add those numbers together. So let's call it like H2O, that would be 2 hydrogens, 1 oxygen. So you look at oxygen, it's 16. You look at hydrogen, it's 1. So your 2 hydrogens, 1 plus 1, plus an oxygen, 16, would give you 18 for the summed atomic masses. Now, formula mass is actually a broader category. It can be molecules, it could be salts, it could be all sorts of things, okay? And really it's just formula meaning whatever formula you're given. And then you sum up the masses. A more specific term, if you're talking about all the atoms in a formula, so simply if you're talking about a molecule, a more specific term would be molecular mass. It's the mass of the molecule. So right here we have different moles. So these are moles of each of these substances, and they've been measured out. So you see here is a mole of helium, here's a mole of copper, here's a mole of carbon. This is the carbon soot that you see when you burn something. This would be a mole of NaCl, which is salt, table salt, and this would be a mole of sugar. Molar volume of a gas. So 1 mole of any gas at STP is going to occupy a volume of 22.4 liters. Now, what is STP? Well, that is standard temperature and pressure. So the standard pressure would be the atmosphere at sea level. So literally the Earth's atmosphere at sea level. And this is a measurement called 1 atmosphere, which is 1 ATM if you want to abbreviate it. And that's because when we try to do these things, we're going to be doing them in labs. Typically, this is going to have the atmospheric pressure of Earth, of course, which is 1 atmosphere. Now, if you've ever noticed, as you go from room to room, the temperatures change all over the place, don't they? And so the standard temperature is actually the temperature of an ice bath, which is 0 degrees Celsius. So literally you take ice, put your thing in it so you can have a nice standard temperature, which is your 0 degrees Celsius. Your standard pressure is just the atmospheric pressure of Earth. That doesn't change that much. Stoichiometry is going to involve the quantitative relationships between reactants and products in a balanced chemical equation. Now that definition sounds a little bit complex. It's not. Stoichiometry is really just using recipes. So remember how I said that if you have 1 hamburger patty, you put it together with 2 sides of a bun, and that gives you a hamburger to eat? That was stoichiometry. Same thing here. So if you have two H2s like we saw before with one O2, you can make two H2Os, two molecules of water. The coefficients of a balanced chemical equation will represent moles. Okay, so when you see those coefficients in your balanced equations, those are most easily talking about and representing moles. So this equation can be read as follows. We have 2 moles of H2 molecules reacting with 1 mole of the O2 molecules to yield 2 moles of the H2O compound or molecules. So let's look at the steps in a stoichiometric calculation. The first step is always to write and balance your chemical equation for the reaction. You need the chemical equation to do anything else. It's how they relate. It's the recipe. It determines everything else. Number 2, determine the molar masses of the substances involved in the calculation. So the next part is, if they give you masses, you're going to have some way of going from those masses to moles. Because remember, the mass of this doesn't necessarily have anything to do with the mass of that. The only thing that's true for masses here is the mass of all your reactants together would equal the mass of all your products together. That's the only thing that's true here. So mass of this does not equal mass of that. In fact, that is not true. Okay? The hydrogen gas would be much lighter than an equivalent number of moles of water. And so, determine the molar masses of the substances involved in the calculation. So for example, if we were doing this for hydrogen, we'd look at hydrogen on the periodic table. It's 1. We have 2 hydrogens, so that would be 1 plus 1. And that would be 2. That would be our molar mass for hydrogen. If we looked at oxygen, well, on the periodic table, oxygen is 16. And so it would be 16 plus 16, or 16 times 2. And that would give you a 32 for the molar mass of oxygen. Again, you don't have to do all of them. You just have to do the ones that you're concerned with, that you're looking at. So the next step is use the coefficients of the balanced equation to convert moles of the given substance to moles of the desired substance. So let's say I gave you that you have 2 grams of hydrogen. That would be 1 mole of hydrogen. The next thing you'll do is, well, I have a mole of hydrogen. That means that I can make a mole of water, because every 2 moles of this will give you 2 moles of that. That means it's a 1-to-1 ratio. Okay? All right, so once we have moles of the desired substance, well, to get grams, if we want to be able to weigh it out or figure out how much we would make, we would have to use the molar mass to convert 2 moles of a desired substance to grams of that desired substance. One of the goals of green chemistry, and green chemistry is something I'll pepper in throughout because we're getting concerned with the environment and ecology more and more these days. So one goal of green chemistry is to reduce waste. One of the ways you can do that is through atom economy. And that is the measured efficiency of a reaction. And so the more efficient a reaction, the less waste you produce. And this would be your atom economy. So the percent atom economy would be the molar mass of the desired product divided by your molar masses of all your reactants added together. And that would tell you how much of the mass you would make into what you want at the end of this, versus how much is going to be left behind as waste you have to dispose of. Right here is a flow chart that shows you the overall flow of doing these stoichiometry problems. Now, solutions. The amount of a solute in a given amount of solvent is defined as solution concentration. So when I talk about a dilute solution, this is going to contain relatively small amounts of solute in a given amount of solvent. So for example, most beverages that you drink are dilute solutions of salt because they have a little bit of salt in them for flavor. A concentrated solution would contain relatively large amounts of solute in a given amount of solvent. Again, solute is the stuff you've dissolved into it. Solvent is what's dissolving in it. So for example, in the previous example, I have salt NaCl. It's the solute dissolved in water, which is the solvent. The salt water, that dilute solution, would be the solution, of course. A concentrated solution would be something like brackish water, which is large amount of salt, 30-something%, dissolved in water. Okay. Molarity. This is typically used by chemists and scientists because it's relating to moles. So molarity, big M, that's how you shorten it, abbreviate it. Big M, be very careful about that because MOL is moles. Small m is something else that I'm not going to get into. And so molarity is big M. This is defined as moles of solute per liter of solution. And so it'll be the moles of solute we have divided by the total liters volume of that solution. Percent concentration. This is actually the solution concentrations you're most familiar with. So percent concentration comes in several varieties. One of the ones you're probably most familiar with is percent by volume. Typically represented as V divided by V when you look on bottles. And so this is going to be the volume of a solute divided by the volume of a solution times 100 to make it a percentage. For example, if I have 5% alcohol on my beer, many of those beers would have been percent by volumes. And so that means that I have 5 milliliters of the ethanol, which is the alcohol in beer, and that is for every 100 milliliters I have of that beer. Okay. Percent by mass. This is actually one of the most common percentages you'll see, especially in industry. This is usually given to you as M over M, which means mass over mass. And so percent mass will be the mass of the solute over the mass of solution. And the reason this is the most common one is it's actually easier to measure masses. You can just put them on balances. You can actually roll them over pressure balances, and bam, you know the mass. Whereas volume is actually usually more difficult to measure, at least on large scales. And so, for example, if you have a percent mass, you might have a percent mass that's like nuts and a mix. And so if you had 10% mass, 10% is macadamia nuts. That means you have 10 grams of macadamia nuts for every 100 grams of your mixture. So right here is a more laboratory example. Here we have reagent grade hydrochloric acid. That means it's the stuff you could use to actually do reactions. This is sold as 38% mass solution of HCl in water. And that would mean for every 100 grams you have of this solution here, you would have 38 grams of it would be HCl. Okay, hopefully that helps. Please make sure you get the homework done. That's what gives me a chance to really look at the questions and see, what you guys need help with. Also, you can always just send me questions, okay? And I'll, help you on them, on the homeworks at least. Won't do it on the test, but on the homeworks, I will always help you with a question. You don't have to answer them first and then wait, okay? Good luck, and bye-bye.